Okay, this is lesson 30 and it's called addition of vectors. A vector is a mathematical idea that has both magnitude and direction. For example, if you're driving a car up a hill, that car has magnitude, the speed of the car, and direction, some angle that it is going at. Or maybe some direction like north, south, east, west that it's traveling at. So a vector is a kind of idea, it's a kind of value that gives you two pieces of information. It tells you the strength or magnitude of the force and the direction of it. So a vector is kind of like a box with a double prize inside. It tells you two things for the price of one. In math and science, we describe forces as vectors because a force has magnitude and direction. So you might try to slide a heavy box across a room. You would be pulling with a certain amount of weight on that box, and that would be the magnitude of your vector, and in a certain direction. So this person in this picture is pulling up on the box a little bit at a certain angle. That's the direction of the force. And then they're pulling with a weight of 30 pounds. That is the magnitude of that force. So a force vector is a thing that tells you two pieces of information about the force and how it's affecting the object that you're applying it to. So, adding vectors. Sometimes we want to add vectors if we want to understand how more than one force is affecting, say, a passenger in a car wreck. Okay, so you've got this car wreck here. You've got this person in the yellow car going straight ahead. All of a sudden, this pink car comes out of nowhere at this angle, going a certain speed. And this this red car is going at a certain speed at that angle. And the car behind is coming at a certain speed at that angle. And this guy's going to come hit at this angle. So all these forces are acting on that yellow car. And if you add all those vectors together with their speed and their direction, you'll find out what the speed and direction of that yellow car will be when it gets all those hits to it. And maybe you'll find out how to make that car safer, or how to make the seatbelt work better, or the airbags, or anything like that. So adding vectors gives you the resultant vector when you have several forces that are acting on an object, and you want to know what the final force is going to be, what the result is going to be of all those forces. So like with this airplane in the wind, the airplane is trying to go straight with a velocity of 100 kilometers per hour. The wind is blowing against it this way at 30 kilometers per hour. And the question is, well, what direction and what speed is the plane actually going to have? Because you got to know how to get it where it's going. So when you add the two vectors, the one of the plane's speed and direction and the wind's speed and direction, you get this resultant vector that tells you which way the plane is going and how fast it's going to be going if those forces are being applied to it. So that's why we need to know how to add vectors. We often use polar coordinates to express vectors, as you would expect, because polar coordinates have a magnitude, that's the r, the radius, and a direction, the angle. So we often use polar coordinates to express vectors. And I want to say one thing about notation. All right. First of all, when I write this, or I hope you all recognize these things as the letter A, even though they look very different. Okay? Why I'm saying that is because you should be able to recognize different ways of expressing the same thing. All right? Now, your book writes polar coordinates like this. That's the notation your book uses. I have never ever seen that notation anywhere else except in Saxon. That is why I am writing it like it really is usually written in other books. Now, I realize there are about 1 million different notations in math that look like this, where you have parentheses and two numbers with a comma in between them. That's the way it is. You have to know the context to know what that means. But this is really the way that vectors are written in polar coordinates in almost every textbook you're ever going to see. So even though you have to know that this is how your book expresses it, and that when you're looking at your answer key, that's what it's going to look like. You need to also know that I'm going to be writing it like this. You can write it like this if you want to. It's just a different notation. It's the same meaning. It means the same thing. I'm only saying this because last time, I think it was on a quiz or something, I used this notation, which I had told you about in class, in your notes. But a lot of people didn't understand it. They didn't know what it was. They were very confused. So that's also a lesson to you that I don't always do everything the same way the book does. And you have to take notes and you have to watch the videos, or you might be lost, because I don't do everything the way the book does it. And sometimes I don't even talk about things that the book talks about. So pay attention in class, take notes, and watch the videos. So I will be writing polar coordinates like this. I also write rectangular coordinates like that. If I have the point 2, 3 on the XY plane, I write it 2, 3. That's rectangular coordinates. Your book would often write that as 2I hat plus 3J hat. I'm trying to use the more standard notations. Getting back to what we were talking about. So, as I was saying, we often use polar coordinates to express vectors because they have a magnitude and a direction. For this particular vector that I just drew, the magnitude is the radius, and in our picture, it's the length of that red arrow, and the direction is the angle, starting at 0 degrees and turning counterclockwise to get to wherever you're going. Even though we may see them in polar coordinates, we can't add them in polar coordinates. The only time we could ever add two vectors without changing them to rectangular coordinates would be if they have the exact same direction, like so their angle might be exactly the same, or if they have opposite directions. That's the only time you can add vectors in polar coordinates, and that's rare that that happens. So usually it's not going to be the case that you can add them while they're in polar coordinates. So to add vectors, first thing you've got to do is change each vector to rectangular coordinates with an X and a Y. Then you're going to add the components to get your new vector. You're going to add the X's, that'll be your new X. You're going to add the Y's, that'll be your new Y. And then you're going to express the resultant vector in rectangular or polar coordinates, depending on what the question asks you to do. So let's look at an example. Find the resultant of 4 20 degrees and 7 negative 230 degrees. And I will just write this here for you, just so you know. That just means we're going to add these two vectors, 4 20 degrees and 7 negative 230 degrees. All right. So as I said, the first thing we're going to have to do is change both of those to rectangular coordinates, which you know how to do already. You've been doing that for a few weeks now. I'm going to draw a picture of these first. So we've got 4 20 degrees. So we're going to go 20 degrees and out 4. And that's going to be our first vector. And then the other vector is 7 negative 230 degrees. So we're going to go clockwise 230 degrees. And then we're going to go out from the origin 7 spaces. All right. All right. Now remember, this is very important. Whenever you are working with a vector and trying to change it into rectangular coordinates, and I've told you this before about changing polars to rectangulars, you have to work with the angle that is between your radius and the x-axis. This is the x-axis right here. So you should always be working with these angles, this one and this one. All right, to change these to rectangular coordinates. And changing them to rectangular coordinates means finding out how to get to this point with an x value, the horizontal part, and a y value. So you're looking for the coordinates of this point that's at the end of the radius. Same thing over here. You've got a point right here. Changing it to rectangular coordinates means you're looking for the x and the y that would take you to that point. All right. And if you always work with the angle between your radius and the x-axis, it will always be true that the radius times the sine of your angle is going to be your y. And the radius times the cosine of your angle is going to be x. But if you don't work with the angle between the radius and the x-axis, you will be confused. Okay, so for the 420, all right, we are looking at the angle between our radius and the x-axis. That's 20 degrees. And so r is 4. It's the length of that radius, that magnitude of that vector. So we know that to find y, we're going to say 4 sine 20 degrees. And to find x, we're going to say 4 cosine 20 degrees. That will give us the coordinates that go here. So you're going to punch that into your calculator. So here you've got your y, which is your second coordinate. That's 1.37. And we're in the first quadrant, so that's positive. And then you're going to punch in 4 times cosine 20. That's going to give you about 3.76. So your x is 3.76. So those are the coordinates of that first vector. Now your book would probably write that as 3.76 I hat plus 1.37 j hat, which you can do. Now we'll look at the other one. The other vector that was negative 230 degrees and 7 for the magnitude, the radius. We know that this angle, theta, that's in the second quadrant, what is it going to be? Well, if you start here at 0, and you go around, when you hit this, you've gone 90 degrees. Now 180. How much further do you have to go to get to 230? Well, 230 minus 180 is 50 degrees. So this angle is 50 degrees. All right, so we've got 7 and we've got 50 degrees. So I'm going to do the x first because it really makes more sense to do the x first since x comes first. So x is going to be 7, that's the radius, times cosine 50 degrees. If you punch that into your calculator, 7 times cosine of 50 is about 4.50. So that's going to go here. And that's not 450. 4.50, and I'm saying 50 because what I got on my calculator, let me write this down somewhere you can see it. What I got on my calculator was 4.4995 and so on. And so if I round this 9 makes this 9 go up, and this 9 makes the 4 go up to 5. The reason I'm putting the extra 0 on there is to let someone know, if they're looking at it, that I rounded it to 2 decimal places, that it really is 4.50, that it's not just that I rounded it to 1 decimal place and got 4.5. I really did go the whole way to the 3rd decimal place to find out what the 2nd decimal place should be. So that's a little bit tricky to understand, but when you need to round something to 2 decimal places, you should show both decimal places so that the person reading it knows it's been rounded to a 2 decimal place accuracy. All right, so let's look for the y. Y is 7 sine 50. And we'll punch that in. 7 times sine 50 is about 5.36. So 5.36. Now, what quadrant are we in? We're in the second quadrant. So x is negative. So we need to put a negative sign in front of the x coordinate. All right, so we have our 2 points, negative 4.50, 5.36, and 3.76, 1.37. These are our 2 vectors. Your book would write that second one as negative 4.50, I hat plus 5.36 j hat. And then add the components. Add the x coordinates, which are the ones with little I hats next to them. So 3.76 minus 4.50, 3.76 minus 4.50 is negative 0.74. So I would, if I were writing it as just regular rectangular coordinates, my x coordinate would be negative 0.74. If you're writing it this way, it would be negative 0.74 I hat. And then for your y coordinate, you would add 1.37 plus 5.36, and that would be 6.73. So I would put that here, 6.73. That would be the new vector in rectangular coordinates, or you could write it 6.73 j hat. We got our resultant vector. We may now want to change it back to polar coordinates. Usually the question will tell you whether they want you to leave it in rectangular or change it to polar. So we will just go ahead and change these to polar. So we will just go ahead and change this to polar. So I'll make a quick sketch of what it's going to look like. All right, it's in the second quadrant, so negative 0.74, so just a tiny bit there, and then up 6.73, so it's going to be like right there, and then it's going to come down like this. Goodness gracious, that's terrible. It's supposed to be a straight line. Yeah, so when we change it to polars, it's going to be this angle and this radius. So this will be our theta and this will be our r right here. But to do that, we need to use this triangle and this angle, the angle between the radius and the x-axis. That is the acute angle between the radius and the x-axis. So this is 0.74 and this is 6.73. So remember, we use tangent, and the theta that I'm going to be working with right now is this angle right here. We always work with the acute angle between the radius and the x-axis. So tangent of theta is going to be opposite, which is 6.73, over adjacent, which is going to be 0.74. So if we do, like I just said, inverse tangent of 6.73 over 0.74, that is going to give me theta, which is about 83.73 degrees. So I've got my theta. Now I need to find my r, and to do that I just use the Pythagorean theorem. So 6.73 squared plus 0.74 squared is equal to r squared. So punch that into your calculator. 6.73 squared plus 0.74 squared, hit equals, then hit the square root sign, and you get about 6.77 for r. So r would be about 6.77, and so you would write your final answer. But wait, what about that theta? Okay, that's not the theta we want, right? We want this angle. So we found this angle, 83.73. So we need to do 180 minus 83.73 to get our angle that goes from 0 to the radius. So 180 minus 83.73 is about 96.27. So we are going to have our final vector is going to have the radius 6.77, and it's going to have angle 96.27 degrees, or your book would write it 6.77, 96.27 degrees. Now, sometimes we want to know what force we'll need in order to counteract the forces that are being applied to an object. This force is called the equilibrant. And sometimes I make a mistake and call it the equilibriant. I cannot remember that it's called the equilibrant because that sounds like such a weird word. But the equilibrant has the exact same magnitude as the resultant, but in the opposite direction. So we're going to do an example, and to find the equilibrant of a vector or a sum of vectors, you have to find the resultant first, and then, so you can see that red arrow is the resultant of adding the two forces F1 and F2. You find the resultant, and then you draw the arrow in the opposite direction, and that is the equilibrant. It's the force that will pull against the resultant and neutralize it. So we're going to look at an example of how you would find the equilibrant, which I may call it the equilibriant. You just have to ignore me, but it's called the equilibrant. Okay, so in this problem, we're going to find the equilibrant of the forces. The two forces where LB is pounds, 4 50 degrees pounds, and -6 170 degrees pounds were applied to an object. Find the equilibrant of the forces. So to do this, the first thing you're going to have to do is find the resultant. So before you can find the equilibrant, you have to find the resultant. And to do that, you are going to first of all graph these two things, 4 50 degrees and 170 degrees, -6, so that's the +6. We want to go in the opposite direction, and we want to use the angle between the 6 and the x-axis is 10 degrees, because we're going 170 degrees, which is just short of 180 degrees by 10 degrees. And then since you have vertical angles, the angle over here in the fourth quadrant is going to be 10 degrees. So these are the two triangles that we're going to be working with. This little triangle here, we're going to find the x and y, and in this triangle, we're going to find the x and y for that. So to do that, we use sine and cosine. So we're going to say for the 4 50-degree vector, we're going to say that x is equal to 4 cosine 50, which is going to be about 2.57. And then y is going to be 4 sine 50, which is about 3.06. And that is in the first quadrant, so x and y are both positive, so that first vector is going to be 2.57, 3.06. The second vector, the one that's 170 degrees and -6, is going to be, we're going to do that the same way. X is equal to 6 cosine 10 degrees, which is about 5.91, and y is 6 sine 10 degrees, which is about 1.04. And since that is in the fourth quadrant, the y is going to be negative, so your x is positive, your y is negative. Okay, so to find the resultant, we're going to add these two vectors. We're going to add the x's to the x's and the y's to the y's. And when we add that, we're going to get 8.48 and 2.02. So this is our resultant. Okay, it's not our equilibrant yet. We're not there yet. Okay, so I'm going to just go ahead and graph the resultant. So I'm going to get rid of all that stuff and graph the resultant. So that's 8.48 over and 2.02 up. And so this is the resultant vector. Now, we don't want the resultant, right? We want the equilibrant. And the equilibrant looks just like the resultant, except it goes in the exact opposite direction. So that's the equilibrant. It points in the opposite direction. So we want to find the x and y for that. And since we know it has the exact same coordinates as this one, except it's in the opposite quadrant, it's in the third quadrant where x and y are both negative, the equilibrant is going to be negative 8.48, negative 2.02. Okay, But we also want to find the polar coordinates of the equilibrant, so we're going to just change the resultant to polar coordinates first. So we're going to take the resultant, 8.48, 2.02, and change that into polar coordinates. So we would do that. We'd find theta and r. So to find r, we're going to use the Pythagorean theorem, 8.48 squared plus 2.02 squared equals r squared. And if we punch that into the calculator and take the square root, we are going to get that r is 8.72. And then to find theta, we're going to use inverse tangent. So inverse tangent of 2.02 over 8.48 is going to be about 13.40 for theta. So the resultant is 8.72, 13.40 degrees newtons. But we don't want the resultant, we want the equilibrant, which points in the opposite direction. So the easy way to write the equilibrant in polars is just to change the direction of the r, make it go in the opposite quadrant. So if this r is 8.72, then if we go in the opposite quadrant, if we use the same theta, but we go in the opposite quadrant, that's going to be negative 0.872. So we can say negative 8.72, 13.40 degrees. So we go the 13.40 degrees, and instead of going this way, the positive 8.72, we go that way for the 8.72. So it's pretty simple to change the resultant to the equilibrant just by using the negative r. And that's going to be newtons. Make sure you show your, make sure you always show your units, because if you don't show units on these notations that I'm using, if you didn't put degrees on these guys right here, you would think they were just coordinate pairs. So you have to make sure you're using the right notation. Okay, in this problem, we want to know what vector force must be added to a force of 20 30 degrees newtons to obtain a resultant of 25 0 degrees newtons. All right, so here's what we're going to do. We're going to say we're going to change these to rectangulars. That's always going to be our first thing we have to do, because we can't add or subtract vectors without changing them to rectangular coordinates. 30 degrees with a length of 20, so 30 degrees here, and r is 20. And then we have 25 0 degrees. So this is 0 degrees, and we're just going out 25. Okay, so for that one, it's pretty easy to write the rectangular coordinates because x is 25 and y is 0. You're not going up at all. So for this one, you can change that to rectangular coordinates just by calling it 25 for your x and 0 for your y. Now, paying attention, this is why it's very important to always put degrees on the angle, because this looks exactly like the polar coordinates. So if you didn't put degrees on the angle for the polar coordinates, you wouldn't realize that that's polar coordinates and these are rectangular coordinates. Okay, so to find the rectangular coordinates for this one, find our x and our y, we're going to use sine and cosine. So 20 cosine 30 is going to be about 17.32, and 20 sine 30 for our y, well, it's going to be exactly 10, because we know that sine 30 is 1/2. Okay, so that these coordinates, 17.32 and 10 for y, go with that vector. All right, so what we need to do, we want to find out what we need to add to that vector to get this vector, because that's what the problem says. what vector force must be added to a force of 20 30 degrees newtons to obtain a resultant of 25 0 degrees newtons. So we need to figure out what x and what y we would add to get 25 0. So we just need to figure out what do you add to 17.32 to get 25. So if we're just working with the x part of this, we'd subtract 17.32 on each side, and we would get that x is 7.68. And then to find y, we'll say 10 plus y is supposed to be 0. So y would be negative 10. So the vector we would add would be 7.68 and negative 10. So this would be the vector we would add, but that's in rectangular coordinates. So we want to change it to polar coordinates. So to change that to polar coordinates, we've got 7.68 negative 10. So down here, I'll write that in polar coordinates. So 7.68, 10. This is the angle we're going to find, and this is r. So to find the angle, we're going to use inverse tangent. So inverse tangent of 10 over 7.68 is going to be about 52.48 degrees. And r, we would find r by using the Pythagorean theorem. 7.68 squared plus 10 squared is r squared, and if you punch that into the calculator and take the square root, you are going to get 12.61. And you can see that this is in the fourth quadrant, so we could write this in polar form by just writing 12.61 for r, and then writing negative 52.48 degrees for our theta. And that would put us right there. So this would be the polar form of the angle you would add to the to 2030 to get 25 0.